Okay, the next section is 6.6, inverse trig functions. So again, to set the stage in the context of inverse functions, we're familiar with the trig functions, and we will discuss some inverse trig functions. And again, they match up, right? They're paired as inverses of one another. So just a really brief acknowledgement of these. I know everyone is familiar, but rather than just jump into the inverse trig functions, I think it does us some good to talk about the original trig functions. So when it comes to the inverses, well, I'll get to that in a second, but I keep mentioning how knowledge of the graph of a function is very useful. So it's pi, that's 2 pi, that's 1, that's -1. So we know this is periodic, right? We know this repeats. This is what we call one cycle, one period. But some characteristics that will help you out with a lot of things, including even the unit circle values. There's a lot of trigonometry that's going to come up in excuse me, chapter 7. So this kind of information is very useful. I mean, you know where the roots are, multiples of pi, and I know where the max is at pi over 2, the min at 3 pi over 2, and I know that the range of this function is just between -1 and 1. That's a useful property that comes up once in a while. So just to know, again, just to know this image, you understand a lot of things about the function. And our old friend here, the cosine, it's the same shape. It's a shifted sine wave. Let's do this. Same information. So the zeros are in different places, the max and min different places, but again, just knowledge of that is good. And the tangent we're going to put in here as well. So a little bit of a different animal. It's not continuous, at least. So that's pi over 2. Couple vertical asymptotes in one cycle of, the tangent function. Similar, kind of the shape of a cubic, although the cubic is continuous everywhere. But you have this shape, and of course it's periodic as well. This repeats. So you notice that I'm leaving out. This says tangent, by the way. I just noticed that's somewhat difficult to read. You know that there's reciprocal functions for these three: cosecant, secant, cotangent, and we're familiar with the graphs of those. We're not going to have discussion of the inverse cosecant, inverse cosecant, inverse secant, inverse cotangent. If you can do these, the inverse sine, cosine, and tangent, you can do those. As long as you understand the concepts, it's fine. They're a little less common, so we're not going to put too much focus on that. So you might remember, let me just go back to this quick. We talked about inverse functions in general. Not every function has an inverse, right? We know that. Which functions have inverses? Functions that are what we call one-to-one, which is a concept from pre-calculus. You know, a function it means it doesn't repeat any output. A function you could see is one-to-one if it were to pass what we'd call the horizontal line test. And we can see, knowing that these repeat, we could see that all three of those would fail that criteria. So the first thought that might pop into your head is, these aren't even one-to-one, how can they have inverses? And that would be a fair statement. So what we do is we cheat a little bit. we cheat for our own devices. So what we do is we're going to consider the three functions that we just had written down. We're going to consider them sine on a limited domain. We're going to restrict the domain so we can get what we want. Sometimes we do that in math. Sometimes we have to make things happen. So let's see if I can draw this nice. Okay, so this would be pi over 2, yeah, that's a point. Pi over 2, 1, and this would be negative pi over 2, negative 1. And if we restrict the domain to just this interval, we are 1 to 1, and we can say we can have an inverse of this. Okay, so it's a little bit of an artificial fix, but so is Kool-Aid, you know. There's no fruit juice in Kool-Aid. Powder. We're going to do the same with cosine. Same idea. Okay, now the tangent we don't have to get too cute with. We just have to make sure that we're considering just one cycle. So we do have to, play this game as well here. And it's the exact same sketch on the last page, just that one cycle. Okay, notice also these are closed intervals. They include the endpoints. This is an open interval because obviously it cannot include the endpoints because the tangent is undefined there. So those are the asymptotes. So what I'd like to do, and I'm going to have this information, I'm going to have this little chart for you. And I hope I can fit this on one sheet. I'm going to abbreviate to save a little space. I'm going to list the trig functions. Okay, so and again, I'm not going to talk about the reciprocal functions. If you can do these three, you can do those three. And I'm going to restrict the domains just like on the last page. When you define a function, the domain is typically implied, but you can dictate what your domain is. So I'm saying that these functions, sine, cosine, tangent, on this domain only. That's what we're defining here. And for each of the three, I'm going to list its inverse. Now there's an interesting thing here that there are two different notations for these three functions. They're the same exact thing. The book goes back and forth freely. They interchange between the two of them without hesitation. I'll probably do the same for the most part. One way is this would be read inverse sine, inverse cosine, tangent. Screwed that up. Inverse tangent. Let's make it x. I don't know why I just made that y. Okay, so inverse sine, inverse cosine, inverse tangent, and likewise, and again, these are the same functions. It's just a different way to write them. Arcsine, arccosine, arctangent. Personally, I prefer these because they stand out more. This looks almost just like this. This little -1 up here. It doesn't really pop. So, yeah, this is not going to fit completely. So I'm going to have to do something here. But we remember that when you have inverse functions, they swap domains and ranges. So the domain of the trig function becomes the range of the inverse trig functions. So these exact intervals are the range. Now, what is the consequence of that? Okay, this is an important point for evaluation. Okay, this is very important for this reason. Let's go talk about what these functions really are and how to evaluate them. I might come back to this one. So if I have, I'm going to write this in a strange, sort of a strange way, but I'm going to say arc trig. So this is my way of representing all three at once. Arcsine, arccosine, arctangent. It doesn't matter. What I'm about to write applies to all three. So the arc whatever, arcsine, cosine, or tangent of x is y. So how do we evaluate that? What does this mean? Think about a trig function. We put in the input into a trig function we think of as an angle, and we get a real number out. This being an inverse is the opposite. So when you are evaluating this, the output here is now, this is the angle. Okay, real number goes in, and an angle comes out. Which angle comes out? So the way you can think about these is the following. This is, if I need to find out arcsine of something, the question is, what is the angle y? What's my output? Whose sine, cosine, or tangent is x? It's like the Jeopardy, that game show where the guys click the thing and talk like idiots. They have the answer, so sort of, and then it's like, what's the question? That's kind of like how this plays out. So what is the arcsine of 0? What angle has a sine of 0? 0. Okay. And I'll go back to this notation. What angle has a cosine of root 2 over 2? Pi over 4. So you might, if you think about this, you might say, well, wait a second. There's a lot of angles that have a sine of 0. Like, what about pi and 2 pi and 7 pi, right? So how do I know what the right answer is? That's where this comes in. Okay, so the correct answers here must reside within these intervals. Okay, so yes, the sine of pi is 0, but it's not within this acceptable interval. This might help. It's very, almost crude memory aid. If I think about the unit circle, right, the sine is the range or the outputs in these two quadrants, the outputs in these two quadrants, and the outputs in these two quadrants. It's a very crude memory aid, but I think some students find it useful. So in other words, if you're asked this question and you put pi, you're incorrect, as far as I'm concerned. Okay? So keep that in mind. That's an important aspect of this. Yes, very important. Okay, let's get a sip of coffee here. I want to address a excuse me, a problem that comes up in trigonometry that we move through pretty quickly. So you've probably seen it. I'm sure you've seen it, but may have forgotten about it. I call this the triangle problem, and this will come up in chapter 7. So it belongs in this section. I want to address it right now. It's a problem. It might look like this. Might be referred to as simplify. Simplify And what it looks like is, let's see, cosine of the arctan, and this can be anything. I'm just going to make it x to make it simple. These kind of nested functions. So this, if you get an expression like this, this is not considered simplified enough as a result. You need to finish this. You need to do what I'm about to do. So again, I call this the triangle problem. What's in parentheses here? This is again an angle. What angle is it? I have no idea. What do I know about this angle? I'm going to call this angle. You don't have to write this obviously, but that's an alpha. So if this is alpha, what do I know about this angle? Nothing except that its tangent is x, or x over 1, right? Opposite to adjacent. So that's what I know about this angle. And if I know two sides, I know the third side, Pythagorean theorem, right? That's our old friend. So this side via Pythagorean theorem looks like this. Okay? Well, what am I looking for here? I'm looking for the cosine of this said angle. And if I know this triangle, I know the cosine, right? Adjacent to hypotenuse. So this is a must-do simplification. You know, of course, there's a variable here because there's a variable here. This is not a numerical value of an angle. This is a variable. See, we get a variable. Okay, so this is the triangle problem. Make sure you know how to do this because this comes up in chapter 7. Okay. What do I want to do? I want to give you some derivative rules. So let's do this. Let's say if y, this is my function of interest. What's y prime here? Well, if y is the inverse sine of x, what does that tell me? That x is sine of y. You can almost think of applying the sine function to each side and having these two cancel. All right, so I'll differentiate, and on the right-hand side, I'm going to have to use implicit differentiation. This is a 1. The derivative of sine is cosine. Since it's a y, I attach y prime, excuse me. And I want to solve this for y prime. So we'll say y prime is 1 over the cosine of y. And what's y? It's that thing. Okay? And now this is the triangle problem. So it comes up in this proof. Obviously, you're not going to be asked to do this proof, but you can see it again now. That's a pretty weak triangle, sorry. This angle has a sine of x, opposite to hypotenuse. What does that mean about this side? Via the Pythagorean theorem, this side is root 1 minus x squared. Okay, so now what is the cosine of this angle, right? This is an angle with a sine of x that provides this side adjacent to hypotenuse. Y prime is 1 over root 1 minus x squared. Okay? The proof, I'm not going to do the cosine one. It's basically identical. What else do I have here? I'll do, this one's a little more, not much different, but I'm just going to show it to you. Let's write it as arctan. I like the way that looks. If that's true, that means this is true. Okay? I should have an arrow there for implies, but you get the point. Okay, differentiating implicitly again. It's kind of the same story. It kind of ends different though. Y, so y prime is 1 over secant squared of y, secant squared of that. Okay? Triangle problem to find out what this denominator should look like. What's in parentheses? An angle. What angle? I don't know. It's got a tangent of x. Opposite to adjacent. Once again, I can now find this side. That's okay. 1 plus x squared under the root. And what is the secant of this unknown, mysterious angle? Well, it's going to be hypotenuse over 1. And notice this is squared, right? So this is, these squares on these functions is bizarre, right? I was never a big fan. But remember what that means, of course. That means you got 2 of these squared, right? So if I square this guy, it's 1 plus x squared. Look okay? All right, let's write them out. Okay, enough of the dog and pony show, right? So derivative rules, new ones. I'm going to use the chain rule, right? I'm going to use the chain rule. I'm looking through my notes to see if I forgot anything here. Okay, I'm just going to use the chain rule. So three derivative rules. I'm going to write them as the arc notation. Obviously, the inverse, it's obviously the same. It's the same function. I just like the way this looks. U, sorry. I don't like the way that looks. That's a U. Arc cosine. Okay? And arctan. And remembering, excuse me, right, U is an expression or a function in X. I don't know why I wrote these so big. It looks ridiculous. Okay, so this will be U prime in my numerator. Right, I could write it out here, but I'm just going to stick it up in there. And this is going to be 1 minus x squared. U squared, I'm sorry. I don't know what my problem is here. Okay? So notice the trig, the trig element is removed. A common thing that you see is the student, who didn't do their homework, they'll write, what will they write over here? Arc cosine, because sine and cosine go together, so they're, it's not. The trig element vanishes. This, interesting, I didn't do the proof for this one. This is the same, it's just negative. And this is, we just did the proof for this one. Sorry, I'm getting a little sloppy here, okay? And I'll write these smaller. We have antiderivative rules. Let's do it like this. Yeah. Okay. Geez, why do I do this? So you notice these are the same with the negatives of each other. So you might ask yourself, well, why can't I say this is negative arcsine? You can. Okay, so if you think along those lines, you're fine. Sometimes I don't mention that because I don't want to confuse people, but someone always asks. Okay, so 3 new antiderivative rules for integration, 3 new derivative rules for derivatives. Okay, let's see a couple examples. Okay? Again, we're just adding another potential flavor to one of the onion layers, right? We're going to start out thinking about what kind of structure we have somewhere within this onion. Probably see those rules that I just ripped that up. I don't know why. Give me a second here. Okay, let's see some derivatives. Differentiate. There's in the homework, there's a few problems. There's a couple triangle problems. There's a couple of just evaluate me. I'm not going to do the evaluate thing. That's just trig. You saw the triangle problems. They all pretty much run the same. Now we have derivatives and antiderivatives. So how about something like this? Y equals arctan of, let's say, the square root of x. Okay, so this is an arctan of u. This is a straightforward one-layered onion. U is the square root of x. So what's u prime? In fact, let's do this. This is sort of what we do when we start differentiation. As you kind of graduate through it, we don't typically see us write this down. Feel free not to. But I see my u prime. And that's my u prime. The rest of it is 1 plus u squared. And that's going to be nice because that's a root. 1 plus x. And I'm fine with this. You could distribute this. Factor, typically the philosophy is factored is better. So what, either way. Not everything has, like when you refer to the back of the book and look up a solution, yours doesn't always have to look just like what's in the back, or doesn't have to look, there's certain things that we always would simplify. Like we never leave this, right? We would always reduce that. That's just laziness not to. This, do I want to distribute it through? It could be a matter of taste. It could be a matter of, what am I going to use this for? Am I going to use it at all? Okay, so not everything has to look the same. I don't know why I just did that. Okay, let's see, what else we got here? How about differentiate? Let's just make it up. X squared arccosine of, I don't know what I'm doing here. I'm just making things up. Okay, so what's the first layer here? This is a product. Okay, so within the product rule, I'll have a simple power rule, and I'll have my new arccosine rule. So I have the first, and the derivative of this thing, my u prime will be 2 square root 1 minus that squared. So I got to square both. And I could write 2x in parentheses in a square, that's fine. I'll clean this up in the next round. So I have first derivative second, plus second derivative first. And I'm going to do a little cleanup here. Not going to save the world or anything, but that looks like hell. Sorry, that's a 4. Okay, so just some new rules. Get used to them. They're a little bit, they're not very aesthetically pleasing, especially since I ripped the paper in half. But, you know, commit them to memory. Put this information on your reference page so you can use these. Let's see some antiderivatives. Again, I just want to reiterate that this chapter, the motivation is to introduce new functions. Some of them I'm sure are new. I know these inverse trig functions are not new. We do this in trig, but the you know, the derivatives and antiderivatives, that's new. But we're just trying to, it's not all about derivatives and integrals, right? Those graphs relate information about their properties. That's information that you need. So just things like that, right? Don't get, calculus is not all about derivatives and integrals. I know that's a huge focus, and that's kind of what makes calculus calculus, but don't forget the other information. Okay, so let's just see a couple of these. I'll just do a few. Let's integrate. What's do? Okay, when you look at an integral, sometimes you think, what does this resemble? This sort of resembles the arctan. Now, there's a 16 there. That's not trivial. That makes it different. So what can I do here? Well, what if I let u be equal to, let's say, let u equal, how do I want to do this? 4x. So why did I choose 4x? Because I don't see 4x here. So you might think that's a strange choice. I don't know why I had to think about that so long. Well, that means u squared is 16x squared. And I see that here. So I can pop in a u squared there. Don't forget du. Okay, what does that mean? That means dx is 1/4 du. So I now have du 1 plus u squared. What is that? That is my arctan derivative. Or, yeah. So this is arctan u. Pop it right in there. Okay? So, what else? Let's see. Integration. Let's see another one. This is kind of the same. Kind of the same. But not. Right, I sort of see the looking out my window. There's a shady person parked out front of my house. Anyway, let's let u be equal to real shady. Anyway, let's let that be my choice of u. That provides du. And this cleans up real quick. Don't forget your negative. Okay, this is du. This is 1 plus u squared. So this is exactly like the last one. So negative arctan. Sorry, that's a little sloppy. Keep this in mind too. Just to make this point, you say, well, you're supposed to simplify that. That's the triangle problem. That is not the triangle problem. The triangle problem has to be this format. It has to be a trig function of an inverse, not the other way. You can't simplify that. Okay, you can simplify that, not that. Okay, that seemed really fast, but that's that. What are you going to do? Have a great day.